Okay, so now we're starting to talk. We've got a section here which is devoted to a very small section of what gases do and what they are. But we do need to look at it. So it has a couple important points in it: mean free path, diffusion, and effusion. And I don't want to spend a lot of time on it. We have a picture here for mean free path. So mean free path, can you see how if you have, this is mean free path, where am I here? Mean free path. If you have particles and they're going through and they're hitting the walls and they're hitting each other, you could see that this particle at this point, say the distance between these two might be L1, and the distance between these two is L2, and the distance between these three is L3, L4, L5. So the average of all of these, okay, is the mean free path. That's the average distance between collisions. The average distance between collisions is the mean free path. All right, and it's I can't imagine how you'd be tested on that other than to say that it's a valuable term and you need to know it. I think the most common question from a section like this is yet to come. I'll show you what that is in a minute, but I need to use this term mean free path. Okay, now diffusion is the next term I want to give you. Oops, that's effusion. Okay, so this is effusion, and I don't think I have a picture for diffusion. Okay, but effusion is when you've got particles that are going from a, what's the definition of effusion? I'm going to page 206 in your book, and it's a process by which a gas escapes from a container into a vacuum through a small hole. Okay, vacuum. Gas escaping. Okay, so effusion is when a gaseous particle or gas escapes from a container into a vacuum through a small hole, and that's what effusion is. All right. And diffusion is when a gas molecules spread out in response, or I say, yeah, diffusion. Man, where's my handwriting going? Diffusion is when gas particles spread out. That's probably enough. They spread out. The rest of the technical term is they spread out in response to a concentration gradient. Okay, so if you have a high concentration, they go from a high concentration to a low concentration. That's diffusion. Okay? All right, those are the only terms I want you to know. Okay, but we want to wrap this up now with Graham's law of effusion. Graham's law of effusion says this. Watch this now. Graham's law of effusion. All right? And that is that the rate of an unknown gas, okay, you know what? Let me write it differently. The rate of gas A, watch this, over the rate of gas B is equal to the square root of the molar mass of the gas. Watch this now. Gas B over molar mass of gas A, right? So the smaller it is, the faster it goes. That's what this means. Smaller it is. Can you see how this I would claim this would fit into a student's head very, very easily. Smaller it is, the faster it goes. That's what Graham's law of effusion says. And this I've seen in many contexts, different textbooks, different tests, and it's virtually always in the context of giving you the rate of one. You look these two up, right, and you calculate the rate of the other. All right? And I think that's what this practice problem has. This is from your book on page 206. So an unknown gas effuses at a rate that is 4.62 times that of nitrogen gas. All right, so we've got gas unknown and gas nitrogen, right? And we know this, that the rate of the unknown gas over the rate of nitrogen is equal to the square root of the molar mass of nitrogen over the molar mass of the unknown gas. What do I got here? Just a second here. Okay, we know that. Okay, so what I got to do is if this is if the rate of the unknown is 4.62 times that of nitrogen, I could just choose something for that and say, oh, that must be 1, or rather, if it's 1, this is going to be 0.462, right? Can you see that? All right, is equal to, and then the molar mass of the of nitrogen is 28.02 grams per mole, right? We've looked that up a bunch of times, so I'm not going to look at it now if you don't mind. So what I'm going to do is I'm going to rearrange this equation and give myself the molar, because that's what it's asking me. What's the molar mass of the unknown gas in grams per mole? So I'm going to rearrange this, and I'm going to say the rate of the unknown rate of N2 squared is equal to the molar mass of nitrogen squared, or not N2, over the molar mass of unknown. Okay? Now I'm going to bring the molar mass of the unknown up here, and I'm going to bring that down here. This is the molar mass of N2 over the rate of unknown rate of N2 squared. Okay, this is easy. Now the molar mass of nitrogen gas is 28.02. It's in grams per mole. So that'll give me that in grams per mole, right? Divided by 0.462 over 1, right? 0.462 over 1 squared. And that, I've run out of space here, is going to give me, you can see how this is one way to find out what a gas is, right? 0.462 squared inverse times 28. Okay, so I get 131.28. 131.28. I have a feeling it's like xenon or something like that. 131.28 grams per mole. I'm going to just check my numbers here real quickly before I move on. 28.02 divided by 0.462 squared equals 131.28. Okay, I think that's right. 131.28. And this is 3 sig figs. And so if that's 3 sig figs, this is 3 sig figs. This is 4 sig figs. This is going to have to be 3 sig figs. So we're going to say this is 131 grams per mole. You know what the next question is, right? The next question is, what is the gas? So I'm going to look this up in the periodic table. And son of a gun, xenon is 131.29. Awesome. So the question doesn't ask what is the gas, but you can see how that would be it. Oh, yeah, question doesn't say what is the gas, but you can see that would be a natural question for it. Okay, that's example 5.15 on page 206, and that's it for mean free path, diffusion, and effusion. Graham's Law of Effusion.